Here's something nobody tells you about the most violent stellar explosions in the universe. They're not really explosions. Not in the way you're picturing. The star doesn't blow outward the way physics predicts it should. It collapses inward, forms a black hole mid-death, and then that black hole, hidden from observation by definition, launches the most energetic event the cosmos is capable of producing. We see the flash. We never see the engine. For most of the 20th century, we didn't even know events like this existed. We're going to change that tonight, piece by piece. New here? Subscribe. Grab something warm. The universe is about to do something very strange, and we're going to watch it together. Part 1. The brightest lie in the universe. For a few seconds, a single point in the sky produces more electromagnetic power than every galaxy, every quasar, every star, and every other source of light in the entire observable universe combined. Not just more than our galaxy, not just more than our local cluster of galaxies, more than all of it. Every photon streaming from every stellar surface across 14 billion light-years of space. And this one thing, this single dying star, briefly outshines all of it at once. And here is where it already gets strange. Because that statement, as staggering as it is not even the most interesting part of what is happening. Let me give you the number, because numbers like this deserve to be spoken out loud, even if the human mind genuinely cannot process them. The apparent luminosity of the most extreme gamma-ray bursts reaches somewhere between 10 to the 51 and 10 to the 54 ergs per second. If you have never worked in ergs before, 1 erg is a very small unit of energy, roughly the amount of kinetic energy in a mosquito in flight. So 10 to the 51 ergs is not a small number of mosquitoes. It is a number so large that writing it out would require following the digit 1 with 51 zeros, and even that act of writing would tell you almost nothing about what it represents. The total energy released by our Sun over its entire 10 billion year lifetime is approximately 10 to the 50 ergs. These events, in a few seconds, release 10 to 100 times that. Now pause on that. Not because it is meant to be frightening, but because what comes next completely reframes what you just read. That number, that incomprehensible wall of energy, is not the explosion. The explosion, in the way you are probably imagining it, comes later. What you are looking at, when you look at that luminosity figure, is the after effect of something that already finished. The real mechanism that produced it happened in the dark, behind a boundary that, by the laws of physics, can never be crossed by any signal, any photon, any piece of information whatsoever. The light we see arrives last, the engine we cannot see fired first. This is the central strangeness of the hypernova. It is not a star blowing outward the way popular science has trained us to picture stellar death. It is, at its core, a star that failed to explode in the conventional sense. A star whose core collapsed so completely, so catastrophically, that it did not leave behind a neutron star or a well-behaved remnant. It formed a black hole. Not as an end state sitting quietly at the center of some debris field, as an active, spinning, violently energetic engine that then used the infalling stellar material around it to power the most luminous flash the universe is capable of producing. Think about the inversion here for a moment, because it is worth sitting with. A supernova, the thing we all learned about, the thing hanging in the corner of every astronomy textbook as the dramatic finale of a massive star, involves material being flung outward, pressure overcoming gravity, the star losing, the outer layers winning and escaping into space. That is the standard death. That is what physics predicts under ordinary circumstances. What happens in a hypernova is almost the opposite of that sequence. The core does not bounce and send a shockwave outward that successfully ejects the outer layers. Instead, the core collapses without a successful outward shock. The star begins to swallow itself. Gravity wins so completely that a black hole forms inside the still intact stellar envelope. And then here is the part that should genuinely disturb your intuition, that black hole becomes the thing that launches the energy outward. The explosion comes from the collapse. The light comes from the darkness. The engine is hidden, by definition, behind an event horizon that no observation can penetrate. You cannot watch it happen. You can only see what it leaves behind. And what it leaves behind, briefly, outshines the entire observable universe. There is a phrase worth introducing now, one that will thread through everything that follows: a star that failed to explode. Hold on to that phrase, because when astronomers first started noticing these events in the data, when the satellites and the telescopes started catching these impossible bursts of gamma-ray energy lighting up the sky, the assumption was that they were seeing bigger supernovae, louder versions of a familiar death. The name they eventually gave to the phenomenon, hypernova, carries that assumption embedded in it. Hyper, meaning above, meaning more, a bigger explosion. But that framing is wrong, and it is wrong in a way that took decades of observation, argument, and theoretical work to untangle. The hypernova is not a louder supernova. It is a fundamentally different kind of stellar death, one where the most important thing that happens is not the outward explosion, but the inward collapse, and one where the most important actor in the entire sequence is something that, by definition, you will never be able to directly observe. We observe the aftermath. We model the mechanism. But the engine itself, the spinning black hole inside the collapsing star, driving jets of relativistic plasma through the stellar material at speeds approaching the speed of light, that engine operates behind a causal boundary that makes it permanently invisible to any instrument we could ever build. So the question this raises is the real question. If the star did not explode in the traditional sense, if the central mechanism is hidden from observation, if what we see is the aftermath rather than the event, what is actually launching the energy? What is producing those jets? What is converting the collapse of a stellar core into the most luminous electromagnetic event in the observable universe? That is the question. And the answer is stranger and more elegant than almost anything else in astrophysics. But before we get there, we need to understand why the term we use for this event is itself a kind of well-intentioned mislabeling, and what that mislabeling tells us about how science actually moves forward when it is chasing something it has never seen before. Part 2. The term that shouldn't exist. The word hypernova did not come from a clean theoretical prediction. It did not emerge from a physicist sitting at a chalkboard and deriving the expected properties of a new class of stellar explosion. It was coined in the late 1990s to describe something the data was already producing before anyone had a satisfying explanation for it, and that is worth remembering, because it means the name arrived before the understanding, and the name quietly embedded an assumption that would slow that understanding down for a while. Before we get to the term itself, it helps to understand the background noise it arrived into. Gamma-ray bursts had been known since the 1960s, though known in the loosest possible sense of that word. They were detected by the Vela satellites, American military spacecraft designed not to study the cosmos, but to watch for nuclear weapons tests in violation of the Partial Nuclear Test Ban Treaty. These satellites were looking for the gamma-ray signatures of detonations. What they found instead were brief, intense flashes of gamma radiation coming from completely random directions in the sky, directions that had nothing to do with any military program on Earth and everything to do with the universe beyond our atmosphere. The Department of Defense declassified this data in 1973, and the astrophysics community immediately began arguing about what these bursts were. For roughly 2 decades, the debate centered on something as basic as distance. Were these events inside our galaxy, or were they extragalactic? The answer mattered enormously, because if they were extragalactic, if they were occurring at cosmological distances, billions of light years away, then the energy required to produce them was almost incomprehensibly large. If they were closer, inside the Milky Way, the energy budget was more manageable, though still extraordinary. The argument went on for longer than it should have, partly because the instruments available at the time could detect the bursts, but could not localize them precisely enough to match them to known objects or host galaxies. The Compton Gamma Ray Observatory, launched in 1991, produced the first real statistical proof that gamma-ray bursts were distributed isotropically across the sky, meaning they showed no preference for the plane of the Milky Way, which strongly suggested they were not happening inside our galaxy. But statistical evidence for extragalactic origin is not the same as a confirmed detection of a specific burst at a specific distance. That confirmation came from an Italian-Dutch satellite called BeppoSAX. In 1997, BeppoSAX detected a gamma-ray burst and then, crucially, localized it precisely enough, within hours, for ground-based telescopes to identify an optical afterglow and measure a redshift. Redshift is the stretching of light as space expands, and it is the primary tool astronomers use to measure cosmological distances. The measured redshift for that burst, GRB 970228, confirmed it was happening at a distance of roughly 6 billion light-years. The energy budget implications were staggering. These were not local events. They were among the most energetic phenomena in the observable universe. And then, in 1998, the piece that makes the term hypernova meaningful fell into place. Astronomers watching a gamma-ray burst called GRB 980425 noticed something unusual. The burst appeared to be spatially coincident with a nearby galaxy, unusually nearby, by gamma-ray burst standards, only about 40 million light-years away. And in the weeks following the burst, a supernova appeared in the same location. Not just any supernova, a supernova with spectroscopic features that set it apart from anything in the existing catalogue. The ejecta were moving at speeds that bordered on relativistic. The kinetic energy implied by the explosion was roughly 50 times larger than a typical supernova. The event was designated SN 1998BW, and it did not fit comfortably into any existing category. Bohdan Paczynski and others began using the term hypernova to describe this class of exceptionally energetic event. The intent was reasonable. These were supernovae that seemed to be operating at a fundamentally higher energy scale, and a new term was useful for flagging the distinction. But embedded in the word was an implicit assumption that the mechanism was the same as a normal supernova just turned up, a bigger version of the same process. That assumption was almost certainly wrong, and the theoretical framework that began to replace it came from a paper by Andrew McFadyen and Stan Woosley, published in 1999, introducing what they called the collapsar model. The collapsar model did not describe a bigger explosion. It described a different kind of death, entirely one centered not on a successful shock revival and outward ejection, but on the formation of a black hole inside the star and the subsequent role of that black hole as an active energy source. The explosion in the collapsar model is not the primary mechanism. The jet launched by the spinning black hole is. The explosion, the supernova we see days later in the optical, is essentially a side effect. This is the gap between the name and the reality. The name implies scale. The mechanism implies a completely different category of event. And the reason this matters for understanding what a hypernova actually is that if you go in thinking about it as a supernova dialed up to 11, you will miss the most important thing happening. You will focus on the outward explosion and overlook the inward collapse that made everything possible. You will see the light and miss the engine. The name hypernova is now standard in the literature. It is not going away. But it is worth holding it slightly at arm's length, knowing that it was coined before the full picture was clear, and that the picture it now describes is stranger and more interesting than the name suggests. Because the star that produced SN 1998BW did not simply explode harder, It collapsed into a black hole, and that black hole, hidden from observation by the event horizon forming inside the stellar interior, launched the energy that we observed from 40 million light-years away. That distinction is everything. And to really feel the weight of it, we need to spend a moment with the numbers. Part 3: Numbers that break intuition. There is a way of thinking about very large numbers that involves comparison, not comprehension. The human mind is not built to hold 10 to the 52 ergs as a felt quantity. It is not a failure of intelligence. It is just that our nervous systems were shaped by an evolutionary environment where the biggest energies we ever needed to track were roughly on the scale of a lightning bolt or a rock slide. What we can do, though, is hold ratios. We can feel the relationship between things, even when we cannot feel the absolute size of either one. So let us try that. A standard core collapse supernova releases approximately 10 to the 53 ergs of total energy. That sounds like a lot, and it is. That single number represents roughly 10 times the total energy our Sun will produce over its entire 10 billion year lifespan. But here is the thing about supernovae that most people do not know. Almost all of that energy, roughly 99% of it, escapes not as light, not as an explosion of gas, but as neutrinos. Ghostly, nearly massless particles that pass through the entire stellar envelope as if it were not there. The visible supernova, the blinding flash of optical light, represents about 10 to the 51 ergs, 1% of 1% of the total energy budget. A hypernova produces roughly 10 to the 52 ergs in kinetic energy alone, energy deposited in the ejector, energy in the outward moving material. That is already 10 times the visible energy of a typical supernova. But the gamma ray burst associated with a hypernova, the flash we detect from across the universe, that apparent luminosity in the gamma ray burst can reach 10 to the 53 or even 10 to the 54 ergs per second for the duration of the burst. That number is what makes these events briefly outshine the entire observable universe in electromagnetic radiation. But here is where the comparison gets more interesting and also more complicated. That luminosity figure, 10 to the 53 ergs per second, is what is called an isotropic equivalent energy. It is the energy you would calculate if the burst were radiating equally in all directions, like a light bulb, and it is almost certainly not doing that. The jets in a collapsar event are narrow, very narrow. They are collimated, focused into beams by magnetic fields threading through the accretion disk around the newly formed black hole. The opening angle of these jets is somewhere between 1 and 10 degrees, depending on the event. To give you a sense of what that means geometrically, imagine taking a sphere and carving out two narrow cones opposite each other, each with an opening angle of maybe 5 degrees. The fraction of the sphere's surface area covered by those cones is tiny, a few tenths of a percent at most. All the energy is concentrated in those cones. None of it is going sideways. This matters enormously for how we interpret the numbers. When we observe a gamma ray burst and measure its apparent luminosity, we are sitting inside one of those cones, looking directly down the barrel of the jet. The jet is pointing almost exactly at Earth, which is why we can see it. If the jet were pointed even a few degrees away, we would miss it entirely. The burst would have happened, the hypernova would have occurred, and from our vantage point in the Milky Way, it would be invisible. The corrected energy, accounting for beaming, drops by a factor of roughly 100 to 1,000. The actual energy in the jet is still extraordinary, something like 10 to the 50 or 10 to the 51 ergs, but it is no longer defying the universe. It is a lot, but it is a bounded lot. The universe is not violating its own energy budget. It is just very, very good at focusing. Now consider what it takes to produce a jet with those properties. The material in the jet is moving at velocities that are easier to express as a fraction of the speed of light. Specifically, the Lorentz factor of the jet, a quantity that encodes how relativistic the motion is, where a Lorentz factor of 1 means stationary and higher numbers mean faster is between 100 and 1000 for the fastest observed gamma-ray burst jets. A Lorentz factor of 100 means the material is moving at approximately 99.995% of the speed of light. A Lorentz factor of 1000 means it is even closer to that ultimate speed limit, close enough that the difference between the jet velocity and the speed of light is smaller than the width of a single hydrogen atom compared to the diameter of Earth. This is not a fast wind. This is not an explosive decompression. This is plasma moving so close to the speed of light that the distinction is almost philosophical, and it is carrying enough energy to briefly outshine the universe when it is beamed in our direction. The ejector in the supernova component, the slower outer layer material being expelled during the hypernova, is itself moving at extraordinary speeds, somewhere between 20,000 and 30,000 kilometers per second. For comparison, a typical Type II supernova ejector moves at around 10,000 kilometers per second. The hypernova ejector is moving 2 to 3 times faster, which in kinetic energy terms translates to 4 to 9 times more energy per unit mass. The broad spectral lines produced by this fast-moving material are actually one of the observational signatures used to classify these events, and we will come back to that when we talk about the 1998 discovery. Then there is the question of rarity. Hypernovae, or at least the subset of them that produce detectable gamma-ray bursts, occur somewhere between once every 100,000 and once every million years per typical galaxy. Our Milky Way, by this estimate, has probably had somewhere between 1 and 10 such events in all of human history. The odds of one occurring close enough and aimed directly at us within the span of a human life are essentially zero. The ones we observe are happening at cosmological distances, hundreds of millions to billions of light years away, and we detect them precisely because their jets happen to be aimed at Earth. There is an additional wrinkle in the rarity calculation that connects back to the central question. Hypernovae appear to be strongly dependent on metallicity, the abundance of elements heavier than hydrogen and helium in the progenitor star. The reason this matters involves stellar winds. Stars with higher metallicity drive stronger stellar winds that carry away mass and angular momentum over the star's lifetime. A star that has lost too much angular momentum by the time its core collapses will not form a rapidly rotating accretion disk around the newborn black hole. Without that rotating disk, there is no jet. Without the jet, there is no gamma-ray burst, and quite possibly no hypernova in the energetic sense. Low metallicity stars retain their angular momentum, and that retained angular momentum is what makes the difference between a star that just quietly collapses and a star that produces the most luminous event in the universe. This has a profound implication. The early universe was almost entirely hydrogen and helium. The heavier elements had not yet been synthesized in sufficient quantities by stellar nucleosynthesis. The first generation of stars, population 3 stars, were forming in an environment of essentially zero metallicity. By the logic above, those early massive stars would have been ideal hypernova progenitors, low metallicity, high rotation retention, and they were likely far more massive than stars forming today. The early universe may have been lit by hypernovae at a rate that modern galaxies cannot match. We cannot see those individual events, they are too far away, and their light has been redshifted beyond easy detection, but the statistical fingerprints of that early energetic period are written into the large-scale structure of the universe in ways we are still learning to read. So what we have is this: an event that briefly outshines the universe, powered by jets moving at essentially the speed of light, produced by a mechanism that is hidden from direct observation, occurring in galaxies with the right chemical composition, and almost impossible to see unless it happens to be pointing directly at you. The energy numbers are real, but misleading in their raw form. The mechanism is real, but hidden. The event is genuinely extreme, but the extremity is focused rather than spherical. If all of that is the output, if those are the observed properties of the aftermath, then the question of what mechanism actually produces it becomes urgent. And to understand the mechanism, we need to first understand what a star is supposed to do when it dies. We need the standard script, the one that physics predicts, before we can appreciate why the hypernova represents such a complete and dramatic departure from it. Part 4. The standard death script. Every massive star, from the moment it ignites to the moment it collapses, is a negotiation between two forces: gravity pulling inward, thermal pressure, generated by nuclear fusion, pushing outward. As long as the star has fuel to burn, the negotiation stays roughly balanced. The star exists as a stable, luminous object because these two forces have reached a working agreement, and then the fuel runs out. The sequence of nuclear burning in a massive star one, with more than roughly 8 times the mass of the Sun, is a ladder descending toward inevitability. The star begins by fusing hydrogen into helium, which is the reaction that powers stars like our Sun and takes billions of years in lower mass stars. In a massive star, the timescale is compressed. A star of 20 solar masses burns through its hydrogen supply in a few million years rather than 10 billion. When the hydrogen in the core is exhausted, the core contracts under gravity, heats up, and initiates helium fusion. Helium burning produces carbon and oxygen. The pattern continues: carbon burning, neon burning, oxygen burning, silicon burning. Each successive fuel produces heavier elements, and each successive burning phase is shorter than the one before, because the energy yield per unit mass decreases as you move up the periodic table, and because the stellar core is getting hotter and denser, and the reactions proceed faster. The hydrogen burning phase lasts millions of years, the helium phase lasts hundreds of thousands, the carbon phase lasts thousands of years, the neon phase lasts a year, the oxygen phase lasts months. The silicon burning phase, the final stage of nuclear fusion, lasts approximately 1 day. At the end of silicon burning, the core is composed primarily of iron and nickel, specifically the isotope nickel-56, which will later decay into cobalt-56, and then iron-56, a decay chain that is responsible for the optical light of the supernova weeks after the explosion. And here is the wall that physics builds at the end of that sequence. Iron is the most tightly bound nucleus in existence. Fusing iron does not release energy, it requires energy. The star has reached the end of the line. There is no next fuel. The negotiation between gravity and pressure is about to end very badly. What happens next takes less than a second, but it reshapes the star completely. With no new energy source to support the core against gravity, the iron core begins to collapse. As it collapses, the density and temperature rise dramatically. At roughly 10 to the 10 grams per cubic centimeter, the photons in the core have enough energy to begin destroying the iron nuclei themselves, breaking them apart into alpha particles and free neutrons and protons through a process called photodisintegration. This process absorbs energy rather than releasing it, which removes pressure support and accelerates the collapse. It is a runaway feedback that makes the collapse happen faster than it otherwise would. Simultaneously, the electrons in the core are being squeezed together with the protons in a process called neutronization, or electron capture. Protons absorb electrons and become neutrons, releasing a neutrino in the process. Vast numbers of neutrinos are produced in this way, and they carry away energy from the core, more energy drain, more pressure loss, more acceleration of the collapse. Within a fraction of a second, the iron core, which has a mass comparable to the Sun, but a radius of roughly 7,000 kilometers, collapses to a radius of about 30 kilometers. The density at the center reaches the density of an atomic nucleus. The matter there becomes what is effectively a giant atomic nucleus, a neutron star in its initial form. At this point, something remarkable happens. The matter reaching nuclear density cannot be compressed further. The neutron degeneracy, pressure, the quantum mechanical resistance to packing neutrons too closely together is immense. The infalling material hits this wall and bounces. It bounces outward as a shock wave propagating through the still infalling outer core. This bounce and the shock wave it produces is the beginning of the supernova explosion. Except it stalls. Almost every time in the simulations, it stalls. The shock wave starts moving outward, but it is fighting against still infalling material, and it is losing energy rapidly. Part of the energy loss comes from the shock itself, dissociating the ion nuclei in the infalling material. The same photodisintegration process that helped accelerate the collapse now costs the outgoing shock energy as it moves through that material. The shock stalls within perhaps 200 milliseconds, sitting at a radius of a few hundred kilometers, neither progressing outward nor collapsing inward, just hanging there. And here is where the standard supernova mechanism becomes interesting in a way that is not widely appreciated. The mechanism that revives the stalled shock, the mechanism that turns a stalled implosion into an explosion, is not fully understood. The leading model involves neutrinos. Remember that the neutron star forming at the center is releasing an enormous flux of neutrinos, carrying away the enormous gravitational energy of the collapse. Most of those neutrinos pass straight through the shock region without interacting with anything. But a small fraction, perhaps a few percent, are absorbed by nucleons in the region behind the shock, depositing energy and adding pressure. Over hundreds of milliseconds, this neutrino heating revives the shock, gives it enough energy to overcome the infalling material, and launches the outer layers of the star into space. That is the standard supernova. It is fragile. It depends on a small percentage of neutrinos interacting in the right place at the right time. And in three-dimensional simulations of core collapse, the explosion often fails. The shock stalls, the neutrino heating is insufficient, and the material keeps falling inward. Many numerical models produce failed explosions even when the input physics is correct to the best of our knowledge. The successful supernova is not a given. It is a barely achieved outcome, a delicate balance that nature often cannot maintain. This is important. The supernova is already a near failure. It is already a case where collapse is nearly winning. The hypernova is what happens when collapse wins completely, when the neutrino heating fails entirely, the shock never revives, and the matter keeps falling inward without producing a conventional explosion. And what happens then is not nothing. It is not a quiet, invisible collapse. It is something that depends entirely on a property of the progenitor star that the standard model mostly ignores: rotation. How fast was the core spinning? The answer to that question determines whether what follows is a gravitational footnote or the most luminous event in the observable universe. Part 5. The failure case. Not all massive stars are built the same way. The progenitor of a typical supernova, the star that eventually explodes in the conventional sense, is often a red supergiant. It has retained much of its hydrogen envelope. It is bloated, extended, rotating relatively slowly. Its core collapses, the shock stalls and revives via neutrino heating, and the star explodes more or less as the textbook predicts, leaving behind a neutron star. The progenitor of a hypernova is a very different kind of object. The star that eventually produces a hypernova is what is called a Wolf-Rayet star, and it is one of the more unusual objects in the stellar zoo. Wolf-Rayet stars are massive, typically between 10 and 40 times the mass of the Sun, though some are considerably more massive, and they are defined primarily by what they have lost. Their hydrogen envelopes have been stripped away, either by strong stellar winds during earlier evolutionary phases or by mass transfer to a binary companion. What remains is essentially the exposed core of a star, a hot, compact, rapidly rotating object composed primarily of helium, carbon, oxygen, and other products of advanced nuclear burning, surrounded by layers of processed material but lacking the extended hydrogen atmosphere of a red supergiant. The absence of the hydrogen envelope matters for a few reasons. It means the star is more compact, which affects how quickly the jet can drill through the stellar material if one forms. It means the star has lower opacity to high-energy radiation, which affects how energy propagates. But the most important thing about a Wolf-Rayet star, in the context of hypernova production, is what the loss of the hydrogen envelope has not removed: angular momentum in the core. Angular momentum, the tendency of rotating objects to keep rotating, is conserved unless something removes it. For stars, the primary mechanisms for angular momentum loss are stellar winds and magnetic coupling between the core and the outer layers. A star with high metallicity drives stronger winds that carry away angular momentum over millions of years. A star that loses its hydrogen envelope early may lose the outer layers that were magnetically coupled to the core, which can actually preserve the core's rotation rather than slowing it. The specifics depend on the exact evolutionary history of the star, the binary interactions it may have experienced, and its metallicity. What matters for the hypernova is this: the progenitor star needs to enter core collapse with a rapidly rotating core. Specifically, the core needs to be rotating fast enough that when it collapses, the angular momentum of the infalling material cannot be accommodated by direct infall onto the central object. The material has too much sideways motion. It has to go somewhere other than straight down. So here is what the failure case looks like from the beginning. The Wolf-Rayet star, after millions of years of evolution, begins core collapse. The iron core implodes, the bounce occurs, the shock forms, so far identical to the standard case. Then the shock stalls. The neutrino heating is insufficient to revive it, perhaps because the stellar core is more massive, perhaps because the rotation changes the neutrino transport, perhaps because of some combination of factors that our simulations still struggle to reproduce in detail. The outer layers of the star, not expelled by a successful shock, begin to fall inward. In the standard failed supernova scenario, which is a different object from a hypernova, worth noting, the infalling material accumulates on the proto-neutron star until it exceeds the mass limit for neutron degeneracy pressure support, typically somewhere between 2 and 3 solar masses. At that point, the neutron star collapses further into a black hole. The entire star may then fall in over the course of seconds to minutes, and from the outside, this looks like a star that simply vanishes, briefly brightening slightly before fading. There are candidate observations of this kind of event, massive stars that disappeared without a conventional supernova. One possible example involved a red supergiant in the galaxy NGC 6946. But in the hypernova progenitor, the story does not end there, because the core has angular momentum, and angular momentum is about to change everything. As the outer layers begin to fall inward, the material with the highest specific angular momentum, the material rotating fastest, cannot fall straight to the center. The centrifugal barrier redirects it. Instead of plunging into the nascent black hole, this material spreads out into a rotating structure around the black hole. The collapse is not spherical, it is not symmetric. The star is being funneled into a disk. Think of it this way. Imagine draining a bathtub, but instead of the water flowing straight down, it has been spinning fast enough that it naturally forms a swirling ring around the drain before it goes in. The drain is the black hole, the ring is the accretion disk, and the formation of that disk is the moment when the physics of the hypernova diverges completely from any version of stellar death that does not involve an active black hole engine. The outer layers of the star are still intact at this point. They are still falling inward, but they have not gone anywhere yet. The black hole is forming at the center. The disk is forming around it. And in the gap between the disk's upper and lower surfaces in the space directly above and below the black hole, along the rotation axis of the system, something extraordinary is about to happen. Part 6. The moment physics breaks. When the proto-neutron star at the center of the collapse exceeds the maximum mass that neutron degeneracy pressure can support, it does not gradually weaken, it collapses. The timescale for this second collapse is fractions of a millisecond. The neutron star, already 10 kilometers across and rotating rapidly, shrinks further, and as it shrinks, the escape velocity at its surface approaches and then exceeds the speed of light. The event horizon forms. An event horizon is not a physical surface. There is no wall there. There is no material boundary you would hit if you fell through it. It is a causal boundary, a surface in space-time defined by the property that light emitted from inside it can never reach the outside. Inside the event horizon, all paths through space-time, including paths that locally feel like they are moving in the outward direction, are bent inexorably inward toward the singularity. You do not feel anything special crossing it. You just can no longer send information out. The event horizon forms at a radius determined by the mass of the black hole, the Schwarzschild radius, equal to 2 times the gravitational constant times the mass divided by the speed of light squared. For a black hole with a mass of 3 to 5 times the Sun, a reasonable initial mass for the central engine of a hypernova, this radius is roughly 9 to 15 kilometers. A sphere of that radius, centered on where the stellar core used to be, is now permanently cut off from the universe outside it. The star, however, does not know this yet. The outer layers of the star, hundreds of solar masses of material, distributed across a radius of perhaps a few solar radii, are still where they were when the collapse began. They are in falling, yes, but the collapse of the core to a black hole happens on a timescale of milliseconds, and the sound speed in the outer stellar material is finite. Information that the core has collapsed cannot propagate outward faster than the local sound speed or the escape velocity of light, whichever is relevant. The outer star is structurally unaware in any physical sense of what just happened at its center. So the star is now divided. At the center, a black hole, perhaps 5 solar masses, with an event horizon roughly 15 kilometers across, surrounded by an accretion disk of infalling material. Beyond the disk, extending outward, the rest of the stellar envelope, still falling inward, still intact, temporarily unaware of the engine forming at its heart. The temperature in the accretion disk at this point is extraordinary, roughly 10 to the 10 Kelvin 10 billion degrees. For comparison, the surface of the Sun is about 6,000 Kelvin. The center of the Sun is roughly 15 million Kelvin. The accretion disk around this newborn black hole is thousands of times hotter than the center of the Sun. At these temperatures, matter and antimatter pairs are being created spontaneously from the thermal energy of the disk. Neutrinos are being produced in vast quantities. The magnetic fields threading the disk are being compressed and amplified by the infall of magnetized material, reaching field strengths that can exceed 10 to the 15th Gauss. 15 billion Gauss. For context, a refrigerator magnet is about 100 Gauss. A strong laboratory magnet is around 100,000 Gauss. The magnetic fields in this accretion disk exceed the strongest fields we can produce in any laboratory by a factor of 10 billion. These magnetic fields are not just intense, they are dynamic. The disk is rotating differentially material closer to the black hole orbits faster than material farther out, the same way inner planets orbit the Sun faster than outer ones. This differential rotation winds up the magnetic field lines, stretches them, twists them, amplifies them further through a process similar to the solar dynamo that generates the Sun's magnetic field. The field lines threading the disk are being stretched into coherent structures, and those structures are going to do something that is, in a way, the single most important moment in the entire sequence. They are going to focus energy along the rotation axis. Along the poles of the system, directly above and below the black hole, in the funnel-shaped region bounded by the inner edge of the accretion disk, the magnetic field lines are threading through the black hole itself. This is not a metaphor. The black hole's own angular momentum and the intense electromagnetic fields around it are creating a region of extreme energy density that is not inside the event horizon, but is immediately adjacent to it. The physics here involves general relativity, quantum field theory in curved spacetime, and magnetohydrodynamics simultaneously. It is some of the most complex physics in the universe, operating in a region that is maybe 10 kilometers across. And out of that region, something is about to emerge that will travel across the galaxy and eventually, billions of years later, reach a satellite in orbit around a distant planet and announce itself as a burst of gamma-ray radiation. The black hole has been born. The engine has started. The star does not know it yet, but it is about to find out. Part 7. Why the star doesn't just disappear. Here is the question that should be nagging at you by now. If the black hole forms at the center of the star and the outer layers are falling inward, why does not the entire star simply fall into the black hole? Why is there a hypernova at all? Why is there a jet, a burst, a flash, an explosion? Why does not the star just vanish, leaving only a black hole surrounded by some cooling gas? The answer is angular momentum. Specifically, it is the fact that angular momentum is conserved, and that conservation, in this context, is catastrophically good at preventing direct infall. Angular momentum is not just a property of the star as a whole, it is a property of every parcel of gas in the star, and it is conserved for each of those parcels unless something exerts a torque on them. When the core collapses, the inner regions fall in rapidly, but the outer regions of the star, particularly the material in the equatorial plane, have been rotating with the star for millions of years. They have accumulated significant angular momentum, and when this material tries to fall directly inward, tries to follow a straight radial path toward the black hole, it finds that its angular momentum will not allow it. Think of it this way. The specific angular momentum of the material in the equatorial plane of the collapsing star, the angular momentum per unit mass, exceeds a critical threshold. That threshold is approximately 10 to the 16th centimeters squared per second. Below this value, material can fall into the black hole more or less directly. Above it, the material cannot reach the innermost stable circular orbit, the closest point where matter can orbit a black hole without spiraling in. It has too much sideways motion. It has to settle into orbit first. This is the formation of the accretion disk in detail. Material falling inward, instead of plunging straight to the center, arrives at the equatorial plane with too much angular momentum to go further inward. It settles into a roughly circular orbit. The next layer of infalling material does the same. Over the course of seconds to minutes, a thick, hot, dense disk of stellar material accumulates around the black hole. The disk extends from near the innermost stable circular orbit, roughly 3 Schwarzschild radii for a non-spinning black hole, closer for a spinning one out to a radius determined by how much angular momentum the infalling material has. For a typical collapsar, the disk might extend to a few hundred kilometers. The disk is not a passive object. It is doing work. The material in the disk is orbiting at relativistic speeds, and because of differential rotation, inner regions orbiting faster than outer regions, there is friction. Magnetic fields threading the disk create viscosity, transferring angular momentum outward through the disk via the magnetorotational instability, a fundamental plasma physics mechanism. This angular momentum transport allows material to slowly spiral inward, and as it spirals inward, gravitational potential energy is converted to heat and radiation. The disk is hot, intensely hot. The 10 billion degree temperature I mentioned earlier is the result of this viscous heating, and it is sustained as long as there is material falling into the disk from the outer stellar layers. Now, the black hole at the center of this disk is spinning. It is spinning because the material that fell into it carried angular momentum and that angular momentum was transferred to the black hole. A spinning black hole is described by the Kerr metric in general relativity, and it has properties that a non-spinning black hole does not. One of those properties is called frame dragging. The rotating black hole literally drags space-time around with it. Like a ball bearing spinning in honey, the space-time in the region immediately surrounding the spinning black hole is being pulled in the direction of the black hole's rotation. This dragging of space-time is not just a curiosity. It defines the region called the ergosphere, a volume outside the event horizon where it is physically impossible for anything, including light, to remain stationary relative to distant observers. Everything in the ergosphere is forced to move in the direction of the black hole's rotation, and this forced motion has an energy implication. A process called the Penrose process and its relativistic variant can, in principle, extract rotational energy from the ergosphere by allowing objects to split within that region, with one piece falling into the black hole and the other escaping with more energy than the original object had. This is real physics. The black hole's rotation is a reservoir of energy that can, under the right conditions, be accessed by the accretion disk and the magnetic fields threading it. And those magnetic fields threading through the ergosphere and the event horizon of the black hole are the specific mechanism by which the Blandford-Znaiec process operates the leading candidate for how the jets in a collapsar event are actually powered. The rotating black hole, in the presence of the disk's magnetic field, acts as a kind of electromagnetic generator. The spinning event horizon threading magnetic field lines is mathematically equivalent to a conductor rotating in a magnetic field, and like a generator, it produces a voltage difference that drives currents, and those currents carry energy. The energy extracted by this process flows preferentially along the magnetic field lines, threading the poles of the system, the regions where the field lines are most organized, where they pass through the black hole and extend upward and downward out of the disk plane. The energy flows along these field lines and begins to accelerate plasma outward along the rotation axis. The disk itself also contributes. The magnetic field threading the disk is being wound up by differential rotation, and this wound-up field also drives material along the rotation axis in the form of a disk wind. Thermal pressure from the extremely hot disk material, combined with magnetic pressure from the amplified field, pushes material upward and downward out of the disk plane. Together, these mechanisms, the Blandford-Znaiec process extracting energy from the spinning black hole, and the magnetically driven disk wind accelerating material from the disk surface, create the conditions for jet formation. Material is being collimated and accelerated along the rotation axis of the system. The jet is not yet formed in the conventional sense, but the energy is flowing in the right direction through the right channel. And above the accretion disk, along the polar axis of the black hole, the pressure from this energy flow is building against the base of what will become the jet. Without the rotation of the progenitor star, none of this happens. Without the angular momentum carried by the infalling material, there is no accretion disk, no differential rotation, no magnetic field amplification, no frame dragging, no energy extraction from the ergosphere. There is only a black hole eating a star in silence. Rotation is the difference between a black hole quietly forming and a black hole launching the most energetic event in the universe. It is, in a very real sense, the switch that turns on the engine. Part 8. The jet. The real explosion. The jet begins to form within seconds of black hole formation, and its formation is not a gentle process. It is a narrow beam of plasma and electromagnetic energy launched from within a few Schwarzschild radii of the event horizon, and it immediately begins drilling upward through the stellar material above it. The physics of jet formation involves several mechanisms operating simultaneously, and the question of which one dominates is still the subject of active research. The Blandford-Znaiec process, operating on the spinning black hole itself, extracts rotational energy through large-scale magnetic fields and converts it into electromagnetic pointing flux, a flow of energy carried by magnetic and electric fields rather than by matter. This pointing-dominated jet is essentially a beam of electromagnetic energy that gradually converts some of its power into particle kinetic energy as it propagates outward. Simultaneously, the magnetically driven disk wind contributes material to the jet base. The hot, dense disk is magnetically accelerated upward along the rotation axis, and this material combines with the pointing flux from the black hole to create a relativistically outflowing column. The magnetic field lines threading through both the disk and the black hole act as a kind of funnel or nozzle, collimating the outflow into a narrow beam. The Lorentz factor of this jet, the measure of its relativistic speed, starts relatively low near the base, where the jet is still dense and the magnetic energy is being converted to kinetic energy. As the jet propagates upward, it accelerates. By the time it would reach the stellar surface, if it survives the transit through the star, the bulk Lorentz factor of the jet material is somewhere between 100 and 1000. Let us sit with a Lorentz factor of 100 for a moment, because it is genuinely strange. A Lorentz factor of 100 means that 1 second of time, as experienced by a particle moving with the jet, corresponds to 100 seconds of time, as measured by a distant observer. It means the kinetic energy of each proton in the jet is 100 times its rest mass energy, which for a proton is about 938 mega-electron volts. At a Lorentz factor of 100, each proton carries kinetic energy comparable to roughly 100 giga-electron volts. The Large Hadron Collider, the most powerful particle accelerator on Earth, produces protons with energies of around 7 tera-electron volts, only 70 times more energetic than each particle in the slower end of these jets. And the Large Hadron Collider is 17 miles in circumference. The jet is carrying protons with energies approaching those produced by the most powerful machine humanity has ever built. But this jet is not a machine. It is a natural consequence of a black hole eating a star. Now, the jet does not simply fly upward into empty space. It has to travel through the entire stellar envelope of the Wolf-Rayet star, which is still largely intact at this point, still falling inward, still structured. The jet has to drill through stellar material that is at nuclear densities near the center and drops off with distance. As the jet propagates through this material, a shock forms where the fast-moving jet material hits the slower stellar material ahead of it. This forward shock pushes stellar material aside and forward, while a reverse shock forms at the jet head and propagates back into the jet material. The shocked stellar material forms a cocoon around the jet, a hot, high-pressure sheath of material that fills the volume around the narrow jet and exerts pressure on it from the sides, helping to collimate it and prevent it from spreading out. The cocoon is important. It is the structure that confines the jet as it drills through the star, and it also deposits significant energy into the stellar envelope in a way that contributes to the eventual supernova-like explosion we observe. The jet drilling through the star is not guaranteed to succeed. If the jet power is too low relative to the pressure of the infalling stellar material, or if the star is too large, the jet can be quenched, choked off, before it reaches the stellar surface. A choked jet deposits all its energy into the stellar interior, producing a particularly energetic supernova-like explosion without a gamma-ray burst. This choked jet scenario is actually thought to be more common than the successful breakout case. Most hypernovae may produce bright supernovae without detectable gamma-ray bursts, simply because the jet died inside the star. We will come back to why this matters for the statistics of observed events. For the cases where the jet succeeds, where the jet power is sufficient and the star compact enough, the jet punches through the stellar surface in a matter of seconds to perhaps a few tens of seconds after launch. The moment of breakout is when the jet material, which has been collimated and accelerated during its passage through the star, suddenly emerges into the much lower density environment outside the stellar surface. And something remarkable happens at that moment. The jet, suddenly free from the confining pressure of the stellar cocoon, undergoes internal shocks. Different parts of the jet moving at slightly different speeds catch up with each other, collide, and produce intense radiation. The magnetic fields in the jet, which have been compressed and amplified during the journey through the star, are now in a region where they can radiate efficiently. Charged particles spiraling around these magnetic field lines emit synchrotron radiation, a form of electromagnetic emission produced when relativistic particles are deflected by magnetic fields. The photon energies produced by this process, for particles with Lorentz factors of hundreds to thousands in magnetic fields of this intensity, fall precisely in the gamma-ray range. This is the gamma-ray burst. It is not the collapse. It is not the black hole forming. It is the jet, seconds after it breaks out of the stellar surface, releasing some of its kinetic and electromagnetic energy as a brief, intense burst of gamma radiation that propagates outward at the speed of light. The duration of the burst, typically between 2 and about 200 seconds for the long-duration class of gamma-ray bursts associated with hypernovae, reflects the duration over which the central engine continues to power the jet. As long as material is falling from the stellar envelope into the accretion disk, the black hole engine runs. When the disk material is exhausted, the jet stops. The gamma-ray burst ends. The burst is moving at essentially the speed of light, and it is beamed. As I described earlier, the opening angle of the beam is a few degrees. If you happen to be located anywhere within that narrow cone, in any direction in space, you receive this flash. From your perspective, it appears as a brief but extraordinarily bright transient in the sky, bright enough, in the most extreme cases, to be barely visible to the naked eye despite originating billions of light years away. If you are not in the cone, the event is effectively invisible in gamma rays. You might eventually detect the optical supernova if you are close enough and if you are watching the right part of the sky. But the defining signature of the hypernova, the gamma ray burst itself, requires you to be looking down the barrel. Part 9. Breakout and the illusion of an explosion. The gamma ray burst is over. 10 seconds, maybe 30, maybe 100. Then it is gone. What is left? The jet, still moving outward into the circumstellar medium, the gas and dust surrounding the star, expelled in stellar winds during the Wolf-Rayet phase, continues to interact with that environment. These interactions produce afterglows. As the jet sweeps up the circumstellar material, the shock it drives decelerates. The decelerating shock accelerates particles, and those particles radiate. The afterglow begins in X-rays, within seconds of the burst ending, and gradually moves to lower energies as the shock slows. Hours after the burst, the afterglow is bright in optical wavelengths. Days later, it is fading but still detectable in radio waves. Weeks later, it may still be detectable with sensitive radio telescopes. Afterglow physics is how much of what we know about gamma-ray burst distances was established. The optical afterglow can be bright enough to measure spectroscopic redshifts, and the redshift gives the distance, and the distance combined with the observed flux gives the luminosity. The geometric structure of the jet, its opening angle, its Lorentz factor, its energetics, can in principle be inferred from the temporal behavior of the afterglow, particularly from something called the jet break, a steepening in the afterglow light curve that occurs when the relativistic beaming angle of the jet becomes comparable to the physical opening angle of the jet. Before the jet break, the observer sees a roughly power law decline in afterglow brightness. After the jet break, the decline steepens. The timing of this break, combined with models of the blast wave physics, constrains the jet geometry. Meanwhile, back where the star was, something else is happening on a different timescale. The stellar material that was not in the jet, the equatorial layers, the outer envelope, the cocoon, has been shocked, heated, and in some cases accelerated outward by the jet passage and the energy deposited in the cocoon. This material is now expanding outward. It is not moving at relativistic speeds. It is moving at tens of thousands of kilometers per second fast by normal standards, but sluggish compared to the jet. It carries the radioactive nickel-56 produced in the inner layers during the explosive nucleosynthesis associated with the shock passage. Nickel-56 is the key to what we see next. With a half-life of about 6.1 days, nickel-56 decays to cobalt-56, which decays with a half-life of about 77.3 days to stable iron-56. Each of these decays releases energy in the form of gamma rays and positrons. In the dense, opaque, expanding ejector, these gamma rays and positrons are absorbed and thermalized, converted to optical light that slowly diffuses outward through the expanding material. This radioactive heating is what powers the optical display of the supernova. Roughly 10 to 20 days after the gamma ray burst, depending on the mass and velocity of the ejector, this optical display peaks. An observer who was not watching at the time of the gamma ray burst, or who is not in the beam, might detect this optical transient without knowing it is connected to a gamma ray burst at all. They would classify it as a supernova, a peculiar one, with very broad spectral lines indicating very fast ejector, highly energetic, lacking hydrogen and helium, features in its spectrum a type I supernova, or, in the most extreme cases, a broad-lined type I supernova. This is the important temporal and causal sequence that reframes how to think about a hypernova. It is worth saying it explicitly. The core collapse comes first, instantaneous by human standards. The black hole forms within the first second. The accretion disk forms over the next few seconds. The jet launches, also within the first few seconds. The jet drills through the star over perhaps 10 to 30 seconds. The jet breaks out and produces the gamma ray burst. All of this, from the first moment of collapse to the gamma ray burst, happens within roughly 1 minute. Then the gamma ray burst propagates outward at the speed of light. The afterglow develops over hours and days, and then, weeks later, the optical supernova peaks. The supernova is the last thing you see. The gamma ray burst comes earlier. The actual mechanism, the collapse, the black hole formation, the jet, happened before either of them, before any detectable light reached an observer. When someone looks up at the sky and says they see a hypernova, what they are seeing is the last echo of a mechanism that was already complete before any photon escaped the stellar surface. The star did not explode in the conventional sense. The star collapsed, formed a black hole, powered a jet, and the jet expelled the outer layers. The supernova is not the cause. It is the receipt printed after the transaction is already done. But here is the problem with everything I have just described. How do we know this is actually what happens? How do we know the collapsar model is correct? We cannot observe a black hole forming inside a star. We cannot watch a jet drill through a stellar envelope. The central engine is hidden, the jet launch region is hidden, and the stellar interior is opaque on the timescales that matter. We are inferring all of this from the photons that eventually escape the gamma ray burst, the afterglow, the supernova, and working backward to the mechanism. How confident can we be in that reconstruction? The answer involves one of the most important observational coincidences in the history of high-energy astrophysics, an event in 1998 that tied the loose ends of the mystery together more tightly than almost anyone expected. Part 10. The 1998 Smoking Gun. On April 25, 1998, an Italian-Dutch satellite called Beppo-Sachs detected a gamma-ray burst, and on the surface there was almost nothing remarkable about it. The burst, designated GRB 980425, lasted about 35 seconds, well within the normal range for a long-duration event. It was not particularly bright by the standards of the instrument. It did not trigger any unusual follow-up protocols. If you had been sitting at a monitoring station, watching the data stream in that day, you probably would have logged it, flagged it for the standard afterglow search, and moved on to whatever came next. Thousands of gamma-ray bursts had been catalogued by this point, and most of them came and went without revealing anything fundamentally new about the universe. This one was different, not because of what it was doing, but because of where it was doing it. The burst's sky position placed it in close proximity to a galaxy called ESO 184, a small, irregular collection of stars located only about 40 million light-years from the Milky Way. 40 million light-years sounds like a lot. In everyday human terms, it is an incomprehensible distance, but in the context of gamma-ray burst astronomy, it is practically in the next room. The vast majority of detected gamma-ray bursts are occurring at distances of billions of light-years events, so remote that by the time their light reaches us, it has been traveling since the universe was a fraction of its current age. GRB 980425. If it was genuinely associated with ESO 184, would be the closest gamma-ray burst ever detected at the time, not by a little, by orders of magnitude. Proximity matters enormously in observational astronomy, for a reason that is almost embarrassingly simple. Things that are closer are brighter. Not intrinsically brighter, the event itself is what it is, regardless of how far away it happens. But the flux we receive, the number of photons landing on our detectors per second, drops off with the square of the distance. An event at 40 million light-years delivers roughly 10,000 times more photons per second to our telescopes than the same event at 400 million light-years. And 10,000 times more photons means 10,000 times more spectral detail, 10,000 times more ability to resolve the temporal structure of the light curve, 10,000 times more opportunity to catch the faint, fading afterglow in every wavelength band we care about. In other words, if this burst was genuinely nearby, astronomers were about to get an unprecedented look at something they had been chasing for decades. And then, in the weeks following the burst, a supernova appeared in the same galaxy. It was designated SN 1998BW, and the moment spectroscopists got their first clean data on it, they knew they were looking at something that did not fit any existing category comfortably. The spectroscopic features of SN 1998BW were extraordinary. To understand why, you need to know a little about how supernova spectra work. When a supernova expands, the material in the outer layers of the ejector absorbs photons from the photosphere below it, creating dark absorption features at specific wavelengths. Those wavelengths are determined by atomic physics. Each element absorbs light at characteristic frequencies, like a fingerprint. In a normal supernova, these features are narrow and well-defined, and you can read them like a chemical inventory of the exploding star. In SN 1998BW, the lines were barely recognizable. They were smeared across broad swaths of the spectrum, blurred almost beyond identification. This is a Doppler effect taken to an extreme. When the material producing those absorption features is moving both toward you and away from you at very high velocities, the spread in those velocities stretches the line across a wide wavelength range. The faster the material is moving, the broader the line. And the lines in SN 1998BW were some of the broadest ever recorded in a supernova spectrum at the time. Working backward from the line width to the ejector velocity gave a number that made people stop and double-check their calculations. The outer ejector of SN 1998BW, at peak light, were moving at roughly 30,000 kilometers per second. Let that number land for a moment. 30,000 kilometers per second. That is 10% of the speed of light. It is approximately 3 times faster than the ejector of a typical core collapse supernova. And because kinetic energy scales with the square of velocity, moving 3 times faster means carrying 9 times more kinetic energy per unit mass. Combined with estimates of the total ejector mass, the total kinetic energy of the explosion came out to roughly 5 times 10 to the 52 ergs. 50 times the kinetic energy of a typical supernova. In one event, that number placed SN 1998 BW in a completely different energy class from any supernova previously observed. And the timing of its appearance in the same galaxy as GRB 980425 within days of the burst was not something that could be dismissed as coincidence. The spatial coincidence was real. The temporal coincidence was real. This supernova, with its extraordinary velocities and its extraordinary energy budget, had appeared essentially simultaneously with a gamma-ray burst in the same small galaxy. The connection was being made carefully, because science does not run on coincidences alone. The association between the burst and the supernova was spatial and temporal, but it was not yet spectroscopic. You could not point to a feature in the supernova spectrum and say, this specific feature was produced by the gamma-ray burst mechanism. The gamma-ray burst was also, frankly, a bit of an odd one, unusually dim for a burst at that distance, roughly 10,000 times less luminous than the most energetic bursts in the catalogue. Some researchers wondered whether it was truly representative of the gamma-ray burst population, or whether it was some kind of unusual, underluminous variant that happened to produce an unusually energetic supernova. The statistical picture was encouraging but incomplete, and then the confirmations started arriving. One by one, in the years that followed, the pattern repeated. Long-duration gamma-ray bursts at relatively nearby distances, followed by supernovae with the same distinctive features as SN 1998 BW, broad absorption lines, high ejector velocities, large kinetic energies, no hydrogen, no helium. The spectra were almost interchangeable from event to event. The most important of these subsequent detections was GRB 030329, caught on March 29, 2003. This burst was about 800 million light-years away, still close by gamma-ray burst standards, still close enough for detailed optical follow-up. The associated supernova, designated SN 2003DH, produced spectra that were so similar to SN 1998 BW that comparing them side by side was striking. The same broad lines, the same high velocities, the same absence of hydrogen and helium, the same energy class. It was as though nature was showing the same card twice, making sure you had seen it clearly. What these events were showing, together, was the observational fingerprint of a broad-lined Type IC supernova. The Type IC classification means the supernova shows no hydrogen lines and no helium lines in its spectrum. The star had lost its outer envelope before exploding, consistent with a Wolf-Rayet progenitor. The broad-lined qualifier describes the smeared, high-velocity spectral features that set these events apart from ordinary Type IC supernovae. And the specific combination of those features with an associated gamma-ray burst gave astronomers something they had been missing, a physical picture they could actually trust. This was the signature of a stripped, rapidly rotating massive star whose core had collapsed, formed a black hole and accretion disk, launched a relativistic jet, and whose outer layers had been blown outward by the jet cocoon exactly as the collapsar model predicted. The collapsar model, developed by McFadyen and Woosley and published in 1999, was written almost in anticipation of what the data were already beginning to show. The model said, take a massive star that has lost its hydrogen envelope, make sure its core is rotating rapidly, let the core collapse, fail to produce a successful outward shock, watch the black hole form and the accretion disk assemble, power a jet through the stellar material, and you will get both a gamma-ray burst and a high-energy, broad-lined Type I supernova. The data said, yes, that is exactly what we are seeing. The match was not perfect, it never is, in the first generation of confirmations, but it was real. What 1998 gave astrophysics was not just a data point, it was a reorientation. Before SN 1998 BW, the gamma-ray burst community and the supernova community were largely operating as separate groups, studying separate phenomena. After it, the connection was established. Long-duration gamma-ray bursts are hypernovae seen face-on, down the barrel of the jet. Hypernovae without gamma-ray bursts are the same events seen from the side, where the jet misses you entirely. The engine is the same. The black hole, the accretion disk, the jet's same mechanism, different viewing angle, different observational signature. Every one of those events, confirmed and accumulated over the years following 1998, is a star that did not explode the way physics predicted it should. Every one of them is a story of inward collapse producing outward energy, of a hidden engine working in the dark, behind an event horizon, launching something that briefly outshines the universe from a place we can never directly observe. The data from 1998 was not just confirmation of a model, it was the first time nature clearly showed us that the intuition was wrong. That the brightest events in the universe are powered by the darkest objects in it, that the light arrives last, and that the engine, by definition, will always be invisible. Part 11. Competing Engines and Broken Models. Here is where it gets uncomfortable. The collapsar model, the spinning black hole, the accretion disk, the Blandford-Znaeck jet is the leading model for long-duration gamma-ray bursts and hypernovae. It fits the observations well. The timescales are right, the energetics are right, the association with stripped-core massive stars is right. The theoretical framework is coherent, the predictions match the data in broad strokes, and the observational confirmations accumulated since 1998 have given the model a degree of empirical support that makes it difficult to dismiss. It is the standard picture. It is what gets taught in graduate astrophysics courses. It is the model that most researchers in the field would defend if you asked them to explain what powers a gamma-ray burst. But there is a fundamental problem with every version of this story, a problem that sits quietly underneath all of those confirmations and all of that theoretical elegance, and that should make anyone intellectually honest at least slightly uneasy. We cannot see the engine, not in the sense that our telescopes are not sensitive enough, though that is also true, not in the sense that we need a bigger mirror or a more energetic detector or a better algorithm for processing the data. We cannot see the engine in principle, because the engine operates behind an event horizon and inside a stellar envelope that is completely opaque to every form of electromagnetic radiation at the timescales that matter. Think about what that actually means. The gamma ray burst, the flash that briefly outshines the universe, comes from the jet after it breaks out through the stellar surface. The afterglow comes from the jet interacting with the circumstellar medium far from the star. The supernova comes from radioactive nickel decaying in the outer ejector weeks after the burst. Not one of these signals originates within the central few kilometers where the actual energy conversion is happening. Not one of them probes the accretion disk, the magnetic field amplification, the frame dragging, the Blandford-Znaeck process. We are inferring all of that from downstream signals. We are inferring the engine from its exhaust. And inferring an engine from its exhaust is a fundamentally different thing from observing the engine directly. This is not a fatal flaw in the collapsar model. Science operates on inference constantly. We infer the interior structure of the Earth from seismic waves. We infer the composition of distant stars from spectral lines. We infer the existence of dark matter from gravitational lensing. Inference built on careful, consistent, cross-checked evidence is how most of what we know about the universe was established. The collapsar model is not standing on weak ground just because we cannot directly observe its central engine. But it does mean that the model has not been proven in the way that a theory is proven when its specific, unique predictions are directly confirmed. And it means that alternative models, if they can also fit the exhaust, if they can reproduce the observed gamma-ray burst properties, the afterglow light curves, the associated supernova characteristics remain viable. You cannot rule out an alternative engine if you cannot observe the engine at all. There is at least one alternative that is serious enough to have attracted substantial support within the astrophysics community, and that fits enough of the data in enough circumstances to be taken genuinely seriously. It is called the magnetar model, and to understand why it is compelling, you need to understand what a millisecond magnetar actually is. A neutron star is what forms when a stellar core collapses but does not quite reach the mass threshold for black hole formation. It is supported against further collapse by neutron degeneracy pressure, the quantum mechanical resistance to packing neutrons too closely together. A typical neutron star has a mass between 1 and 2 times the mass of the Sun, but a radius of only about 10 kilometers. The density is extraordinary. A teaspoon of neutron star material would weigh roughly 1 billion tons on Earth's surface. Neutron stars also rotate, sometimes very rapidly, and they carry magnetic fields. A millisecond magnetar is a neutron star pushed to extremes in both of those properties simultaneously. It rotates approximately once per millisecond, roughly 1,000 times per second, which means its equatorial surface is moving at a significant fraction of the speed of light. And it carries a magnetic field of around 10 to the 15 Gauss. To give you a sense of what that means, the strongest sustained magnetic fields produced in any laboratory on Earth are around 45 Tesla, or about 450,000 Gauss. The millisecond magnetar's field exceeds that by a factor of roughly 2 billion. It is a spinning ball of nuclear density matter the size of a city, rotating 1,000 times per second, wrapped in a magnetic field 2 billion times stronger than anything we can produce. It is one of the most extreme objects the universe is capable of creating short of a black hole, and it is an extraordinary reservoir of energy. A millisecond magnetar carries roughly 10 to the 52 ergs of rotational kinetic energy, the energy stored in its spin. That is the same order of magnitude as the total energy budget of a gamma-ray burst. As the magnetar spins down, as its rotating magnetic field radiates electromagnetic energy into its surroundings, gradually decelerating the neutron star, that rotational energy is available to power outflows. The spin-down luminosity of a millisecond magnetar can be channeled into a jet through the same magnetic mechanisms that operate in the collapsar model, or it can inflate a hot bubble of relativistic material inside the stellar envelope that eventually breaks out and drives the explosion. The timescales work. For reasonable combinations of initial spin period and magnetic field strength, the spin-down time of a millisecond magnetar falls in the range of seconds to minutes, which is exactly the range of long-duration gamma-ray burst durations. The energy budget works. The rough geometry works. The magnetar model can, in principle, reproduce the basic observable properties of a gamma-ray burst without invoking a black hole at all. And the magnetar model has a specific observational advantage that the pure collapsar model struggles to match. It is called the plateau phase. After the initial gamma-ray burst emission ends, the X-ray afterglow typically begins declining. In the simplest external shock model, you would expect that decline to follow a smooth power law from the start, the blast wave sweeping up circumstellar material, gradually decelerating, the shock-accelerated electrons gradually losing energy. But a large fraction of observed gamma-ray burst X-ray afterglows do not behave this way. Instead, they show a period of roughly constant flux lasting anywhere from 100 to several thousand seconds after the burst, before the steeper decline finally sets in. This plateau is real, it is common, and it does not fit naturally in a model where the only energy source is the initial explosion. It fits very naturally in the magnetar model. A magnetar spinning down at a roughly constant rate injects energy into the blast wave at a roughly constant rate, maintaining the X-ray flux at an elevated level until the spin-down rate drops below the threshold needed to sustain it. When that happens, the injection stops and the afterglow steepens. The plateau ends. The timing and duration of the plateau, in this picture, directly reflect the spin-down timescale of the magnetar, a property of the central engine encoded in the light curve of the afterglow. This is the kind of specific, falsifiable connection between model and observation that makes a theory scientifically useful, and the magnetar model makes it clearly. So the magnetar model is not wrong. It is not a fringe idea maintained by a stubborn minority against the weight of evidence. It is a serious model supported by real observations. And the question is not whether it can produce gamma-ray burst phenomenology, it clearly can, but whether it is actually operating in real events, and if so, in which ones. This is where the models begin to hybridize in ways that are theoretically fascinating and observationally almost impossible to distinguish. There is a class of models in which the magnetar is not a stable final state, but a transient phase. The core collapses, the proto-neutron star forms, and the collapse imparts rapid rotation, potentially millisecond rotation to the neutron star during its formation. The magnetar phase begins. The neutron star is powering the early jet, driving the early emission, but the neutron star is massive. It is sitting at the upper end of the mass range that neutron degeneracy pressure can support, and it is accreting material from the disk forming around it. Every second it survives, it is getting heavier. Eventually, and the timescale here depends on the accretion rate and the initial neutron star mass, and could be anywhere from a few seconds to several minutes, the neutron star crosses the maximum mass threshold and collapses further into a black hole. The transition is essentially instantaneous. One moment there is a neutron star, the next moment there is a black hole, an accretion disk, and the Blandford-Znaiec process firing up. The jet that was being powered by magnetar spin-down is now being powered by black hole accretion. The engine has changed mid-burst. The gamma-ray burst continues, but the character of the emission might shift the early chaotic, spiky emission associated with the magnetar phase, giving way to a smoother, more sustained emission associated with the more stable black hole accretion phase. Some gamma-ray burst light curves do show exactly this kind of behavior. Early emission that is variable and irregular, with rapid flares and complex temporal structure, transitioning to a more sustained phase that declines more smoothly. Whether this reflects a magnetar to black hole transition or simply the variability of a black hole accretion disk in a turbulent environment is, at present, impossible to determine from the observations alone, because we cannot see the engine. We are still reading the exhaust. The choke jet scenario introduces yet another dimension of complexity, and it connects the hypernova story back to something larger, the question of how common these events actually are, and how often we are missing them entirely. If the jet, launched by the central engine, whether that engine is a black hole or a magnetar, does not have enough power to drill through the stellar envelope, or if the star is too extended for the jet to traverse before the engine runs out of fuel, the jet dies inside the star. It deposits all of its energy into the stellar interior, the cocoon of shocked material that formed around the jet as it was drilling through expands outwards spherically, driving a shock wave through the outer layers of the star, blowing them outward. From the outside, this looks like a very energetic, asymmetric supernova, a broad-lined Type IC supernova with high ejector velocities and large kinetic energy but no gamma-ray burst, because the jet never made it to the surface. This choked jet scenario is now thought to be extremely common, possibly the dominant outcome of the hypernova mechanism. For every gamma-ray burst we detect, current estimates suggest there may be 10, 50, or even 100 jet-driven stellar explosions happening where the jet was quenched inside the star. We classify those events as broad-lined Type IC supernovae. We catalogue them. We measure their spectra and their light curves and their kinetic energies. and we do not connect them to gamma-ray bursts, because no burst was detected, because no burst escaped. This is the population mismatch problem stated plainly. The observed rate of long-duration gamma-ray bursts, even after correcting for beaming, even accounting for the fact that we only see the fraction of events pointed at us, is significantly lower than the observed rate of broad-lined typic supernovae. If the mechanism is the same in both cases, then most of the mechanism is invisible to us as a gamma-ray burst. The hypernova is not rare. The gamma-ray burst is rare. The mechanism happens frequently. The announcement only goes out sometimes. What this means for the central story is worth stating directly. Every viable version of the model, the pure collapsar, the magnetar, the hybrid, the choked jet, shares the same basic architecture. A massive star whose core has collapsed. A compact object at the center, either a black hole or a millisecond magnetar. Rapid rotation, strong magnetic fields. Energy extraction from that rotation channeled into an outflow. The differences between the models are real and scientifically important. But they are differences in the identity of the engine and the details of how the energy is channeled. The core narrative, a star that failed to explode conventionally, a hidden engine converting rotational energy into the most luminous events in the universe, is the same in every version. We are not arguing about whether this kind of death happens. We are arguing about the exact mechanism at the center of it, in a region 10 kilometers across, behind an event horizon, inside a stellar envelope, at distances of billions of light years. The universe is doing something extraordinary at the center of these events, and we are still arguing about exactly what. Part 12. The Other Hypernova and the Edge of Physics. Everything described so far, the collapsar, the black hole engine, the relativistic jet drilling through the stellar envelope, the gamma-ray burst announcing itself to the universe, represents one branch of what astrophysicists call hypernova-class events. It is the branch that produces gamma-ray bursts. It is the branch connected to the most luminous transients in the observable universe, the branch where a hidden black hole engine converts the rotational energy of infalling stellar material into the most focused, most energetic electromagnetic outburst the cosmos is capable of producing. That branch has a coherent theoretical framework, an accumulating body of observational evidence, and a clear narrative. A star that failed to explode conventionally collapsed into a black hole mid-death, and let that black hole finish the job from the inside out. But there is another class of event that sometimes receives the hypernova label, and it operates on a completely different physical mechanism, one that does not involve a black hole at all, at least not directly, and one that produces an explosion so total, so complete, so thoroughly catastrophic that it leaves absolutely nothing behind. No neutron star, no black hole, no cinder, no remnant of any kind. Just an expanding cloud of gas and newly synthesized elements spreading outward into the interstellar medium, carrying the chemical legacy of a star that no longer exists in any coherent form. This other branch involves stars that are not just massive, but extraordinarily massive. We are talking about objects with masses somewhere between roughly 130 and 250 times the mass of the Sun. To put that in perspective, the Wolf-Rayet stars that produce collapsars already among the most massive stars in any modern galaxy typically range from 10 to 40 solar masses. The stars capable of triggering this second mechanism are 3 to 10 times heavier than that. They represent the extreme upper end of the stellar mass function, rare even by the standards of massive stars, forming only in environments where the conditions for accumulating truly extraordinary amounts of mass during star formation happen to align. In the modern universe, such conditions are unusual. In the early universe, they may have been common. The evolution of a star in this mass range begins similarly to lower mass stars. Hydrogen burning proceeds through the main sequence, producing helium. Helium burning follows, producing carbon and oxygen. Carbon burning advances the nuclear processing further. The core contracts and heats between each burning phase, and the star builds up a layered internal structure of progressively heavier elements surrounding the iron group core that is the inevitable destination of all stellar nucleosynthesis. Up to this point, the story is recognizable, different in scale, but recognizable in outline. Then the core temperature climbs toward approximately 7 times 10 to the 9th Kelvin, 7 billion degrees. And at that temperature, in a star of this mass, something happens that does not occur in lighter stars, because lighter stars never get their cores hot enough to trigger it. The photons, permeating the core gamma-ray photons, carrying the thermal energy of the interior, reach energies sufficient to spontaneously create matter from pure electromagnetic radiation. Specifically, they produce electron-positron pairs. A single high-energy photon converts into an electron and its antimatter partner, a positron, through a process that is entirely consistent with the laws of quantum field theory, and that happens constantly in particle accelerators on Earth. But that has never before, in this star's history, occurred at anything like the rate it is now occurring. This is pair production, and it seems, at first glance, like a relatively minor thing. Electrons and positrons are tiny. They carry little momentum compared to the photons that created them. Why should their creation matter to the structural stability of a star hundreds of times more massive than the Sun? The answer lies in what is no longer there after the conversion happens. The photons that created the pairs are gone. They no longer exist as photons. They have been converted into matter, and while that matter carries energy, it does not contribute to radiation pressure in the same way that photons do. Radiation pressure, the outward push of light against the stellar material, is one of the primary forces holding the core of a very massive star up against gravity. In ordinary stars, this pressure is stable because the photon population is in equilibrium with the temperature. But in a star hot enough for widespread pair production, photons are being continuously removed from the radiation field and converted into particle pairs. The radiation pressure drops. The support against gravity weakens. Gravity responds immediately. The core begins to contract. The contraction increases the temperature. The higher temperature produces more energetic photons. More energetic photons undergo pair production more readily. More pairs form, more photons disappear. Radiation pressure drops further. The core contracts faster. This is the pair instability, and once it begins, it does not stop on its own. It is a runaway feedback loop with no natural break, a thermodynamic cliff that the core falls off with increasing speed. But here is where the pair instability supernova diverges completely from the collapsar, and where the story takes a turn that the collapsar narrative does not. In the collapsar, the collapse continues all the way to a black hole, with the outer layers eventually being expelled by the jet. In the pair instability supernova, the collapse does something different before a black hole can form. As the core contracts catastrophically under the pair instability, the oxygen and heavier elements compressed into the shrinking core reach the temperatures and densities required for explosive thermonuclear burning. Not gradual burning, the kind that powers stars over millions of years. Explosive burning, the kind that releases enormous amounts of energy on timescales of seconds. The thermonuclear energy released in this runaway burning is not merely enough to halt the collapse. It is not merely enough to push the outer layers outward while leaving a compact remnant behind. It is enough to unbind the entire star. Every gram of material, from the innermost nuclear processed core to the outermost hydrogen pore envelope, receives more than enough energy to exceed its local escape velocity. The entire star explodes. Not the outer layers, not the envelope. The entire star, core and all, in a single catastrophic thermonuclear detonation that completes on timescales of seconds to minutes and produces a shock wave that propagates outward through every layer of the stellar structure simultaneously. When the shock wave reaches the surface and the explosion is complete, there is nothing left. The pair instability supernova is the only known mechanism by which a star can die and leave zero remnant of any kind. Every other stellar death leaves something behind. A white dwarf, a neutron star, a black hole, even a dense cloud of debris. The pair instability supernova leaves only absence and an expanding shell of gas carrying the synthesized elements of millions of years of stellar nuclear processing. The energy released can exceed 10 to the 53 ergs, potentially larger than even the most energetic collapsar events. But there is a crucial difference in how that energy is distributed. The collapsar concentrates its energy in a narrow, relativistic jet, beaming it across billions of light years in a focused corridor of gamma radiation. The pair instability supernova releases its energy spherically, spread across all directions equally. The total energy may be comparable or even larger, but without the beaming, the luminosity per unit solid angle is far lower. The result is not a gamma-ray burst. It is an extraordinarily luminous optical transient, a supernova that can outshine its entire host galaxy for months, powered by the enormous quantity of radioactive nickel-56 synthesized in the thermonuclear explosion. While a typical core collapse supernova synthesizes perhaps a tenth of a solar mass of nickel-56, a pair instability supernova can produce several solar masses of it. The radioactive decay of that nickel and the subsequent decay of the cobalt-56 it produces powers an optical display that can persist and remain detectable for years rather than weeks. The best observational candidate for this mechanism currently in the literature is a supernova designated SN 2007bi, detected in 2007 in a small dwarf galaxy located roughly 1.7 billion light-years from the Milky Way. The light curve of SN 2007b was extraordinary. It brightened to a peak absolute magnitude that made it one of the most intrinsically luminous supernovae ever recorded at the time of its detection, and then it declined unusually slowly, on a timescale consistent with the decay of a very large mass of radioactive nickel-56. The inferred nickel mass was roughly 3 to 4 solar masses, compared to the typical tenth of a solar mass in a standard supernova. The modelling of the progenitor suggested a star with an initial mass somewhere between 100 and 200 solar masses, with a final pre-explosion mass of roughly 100 solar masses after wind-driven mass loss during its evolution. These numbers sit comfortably within the theoretical pair instability mass range. SN 2007bi is not universally accepted as a confirmed pair instability supernova. Alternative models involving a pulsed magnetar engine can also reproduce some of its observed properties, and the data quality, while impressive, does not definitively rule out all alternatives. But it is the most compelling observational candidate currently available, and its properties are consistent with what the pair instability mechanism predicts in enough independent ways that most researchers treat it as a strong candidate, if not a confirmed case. Between the collapsar mass range and the pair instability mass range, there is an intermediate zone that produces a third category of behavior. Stars with masses roughly between 40 and 130 solar masses occupy a region where neither mechanism operates cleanly. These stars are massive enough to trigger pair instability, but not massive enough for the thermonuclear energy released during the instability to completely unbind the star in a single event. Instead, the pair instability triggers a partial explosion. Enough energy is released to expel some outer layers and reverse the collapse temporarily, but the core survives. The star then contracts again, reheats, triggers pair instability again, partially explodes again. This cycle can repeat multiple times, with each episode ejecting a shell of material into the circumstellar environment. The shells pile up around the dying star, creating a dense, structured cocoon of expelled material. Eventually, enough mass is lost through these repeated pulsations that the remaining stellar mass falls below the critical range for pair instability, and the star undergoes a final collapse. The final collapse may produce a conventional supernova or a collapsar-type event, depending on the remaining mass and the rotation state of the core. When the final explosion plows into the circumstellar shells that were ejected during the pulsational phase, the interaction between the blast wave and that dense surrounding material produces an extraordinarily bright optical transient, sometimes called a superluminous supernova, that can reach luminosities 10 to 100 times, greater than a typical supernova. Several of the superluminous supernovae observed in recent years may be explained by exactly this pulsational pair instability mechanism. Though again, the alternative magnetar model competes as an explanation for some of them. Now extend this picture back to the beginning of the universe, and the implications become genuinely strange. The first generation of stars, population 3 stars, forming in the universe's first few 100 million years, formed in an environment of essentially pure hydrogen and helium. The heavier elements that serve as cooling agents in modern star-forming clouds, enabling those clouds to fragment into smaller, lower-mass stars, simply did not exist yet. Metal line cooling, dust cooling, molecular cooling by carbon monoxide, none of these mechanisms were available to the first collapsing gas clouds. Without efficient fragmentation, the mass scales available to individual protostars were larger. Population 3 stars may have routinely reached hundreds or even thousands of solar masses. The simulations disagree significantly about the exact mass distribution, and direct observation of population 3 stars is not currently possible. They formed too long ago, and any individual star from that generation has long since died. But the theoretical arguments for very high masses are robust. A population 3 star of several hundred solar masses, forming in an environment of zero metallicity, would have retained essentially all of its angular momentum, no metal-driven winds to carry it away. If its final mass at the time of collapse fell in the collapsar range, it would have produced a hypernova with energetics potentially exceeding anything we observe in the modern universe, powering a gamma-ray burst that would have been detectable across essentially the entire observable universe if it were pointed at us. If its mass fell in the pair instability range, it would have exploded completely, synthesizing and dispersing several solar masses of heavy elements into the primordial intergalactic medium in a single event. These heavy elements, carbon, oxygen, silicon, iron, nickel, would have dispersed through the surrounding gas, been incorporated into later generations of stars and the planets forming around them, and ultimately ended up in chemistry, biology, and geology billions of years down the line. The atoms in your body were not made in the Big Bang. The Big Bang produced hydrogen and helium and a little lithium. Everything else was made in stars, and some of that everything else a fraction of the carbon in your cells. A portion of the oxygen you are breathing right now may have been synthesized in a pair instability supernova during the first billion years of the universe, in a star so massive it could not exist in the modern galaxy, exploding so completely that it left nothing behind except the elements it scattered into space. The black hole mass gap, discovered by gravitational wave astronomy, adds another thread connecting hypernovae to fundamental open questions. LIGO and its partner detectors have identified merging black holes with masses in the range of roughly 40 to 150 solar masses, a range that should, according to the pair instability models, be empty. Stars that would form black holes of these masses should instead trigger pair instability, explode completely, and leave no remnant at all. The mass gap should be a desert. LIGO found it populated. Some of these intermediate mass black holes likely formed through hierarchical mergers. Two smaller black holes merging in a dense stellar environment like a globular cluster, their product exceeding the mass that any single star could have left directly. Others may reflect evolutionary pathways through binary star interactions, or stellar physics that modifies the pair instability threshold in ways not fully captured by current models. And some may reflect the pulsational pair instability channel, where a star loses enough mass through repeated pulsations to leave a remnant that falls just below the mass gap, or where the pulsational stripping alters the rotation and composition of the core enough to change how the final collapse proceeds. Hypernovae and their variants, through their influence on how massive stars lose mass, retain angular momentum, and ultimately collapse or explode, sit at the intersection of all of these unresolved puzzles. What determines whether a given massive star ends as a standard supernova, a collapsar, a pair instability supernova, a pulsational event, or a simple failed supernova with no explosion at all? The answer depends on a combination of initial mass, metallicity, rotation rate, binary interactions, and probably several factors we have not yet identified or correctly weighted in our models. The dividing lines between these outcomes are not sharp boundaries. They are fuzzy regions, where small differences in initial conditions can lead to dramatically different deaths. And since we cannot watch the central event directly in any of these cases, since every observation is of the exhaust rather than the engine, the uncertainty compounds. These are the actual open questions at the frontier of high-energy astrophysics. Not rhetorical questions used to create dramatic tension, but genuine unsolved problems with real researchers, real telescopes, and real theoretical programs aimed at resolving them. And at the center of all of them, whether the mechanism is a collapsar or a pair instability explosion or a pulsational event, whether the engine is a black hole or a magnetar or a thermonuclear detonation, the same uncomfortable truth applies. The most extreme stellar deaths the universe produces are the ones we can observe least directly. The most energetic events leave the most indirect evidence. The most luminous flashes come from the most inaccessible engines. Something extraordinary is happening at the center of these events. We have very good reasons to believe we understand the broad outlines of what it is, and we will probably never be able to directly confirm it. That gap between what we know and what we can verify is not a failure of science. It is where science actually lives. Epilogue: the light we were not supposed to see. Let us end where we began, but with different eyes. A gamma-ray burst alert arrives at a satellite, a signal of a few seconds to perhaps a few minutes, arriving from a direction that was indistinguishable from empty sky moments earlier. The satellite calculates a position. Ground-based telescopes swing to that part of the sky. They catch the fading afterglow. Days later, they watch a supernova rise and fall. The story is assembled from fragments, from the aftermath of something that finished before any of those photons were emitted. And the event that produced all of it happened in the dark. A star, perhaps 40 times the mass of the Sun, perhaps in a galaxy 2 billion light years away, evolved over millions of years, shed its hydrogen envelope, built up an iron core, and began to collapse. The core exceeded the neutron degeneracy limit. A black hole formed. An accretion disk formed. Jets launched. The jets drilled through the star. Photons escaped. By the time you detect anything at all, by the time any electromagnetic signal from that event reaches any instrument we have built, the event is over. The black hole is sitting at the center of an expanding cloud of debris, accreting the last of the disk material, already old in the timescale of the mechanism that produced it. The jets have long since propagated outward at nearly the speed of light, carrying the gamma-ray burst ahead of them. The supernova is still brightening, powered by nickel-56 decaying in the expanding ejector. None of it shows you the engine. None of it reaches through the event horizon. None of it tells you directly what happened in those first few seconds in the disk, at the boundary where space-time curves into an unreachable interior. You are watching the receipt for a transaction that happened in the dark, and the receipt is brief and blinding and gone in seconds, but it is all you get. There is something in that constraint worth sitting with, not as a frustration, but as a fact about the universe. The most energetic events in the cosmos are engineered around an inaccessibility. The most luminous flashes in existence are produced by engines that, by the laws of general relativity, cannot be directly observed. The universe is performing its most extreme feat and hiding the mechanism behind the one boundary that is guaranteed to hold forever. Not because of practical limitations of our instruments or our engineering, because causality itself draws a line there. We can know that a black hole formed. We can infer its mass and spin from the properties of the jet and the accretion disk. We can model the physical processes operating in its vicinity with extraordinary precision. We can write down the equations that govern what happens inside the event horizon, at least for the first fractions of a second before quantum gravitational effects become important. But we cannot verify those equations by observation, because the verification would require a signal from inside the horizon, and no such signal can exist. The gamma-ray burst is, in a very literal sense, a message from the edge of knowability. It is the last thing that escaped before the event horizon closed around the engine. It is the universe saying, in photons instead of words, something extraordinary just happened here, at a place you will never be able to see, using a mechanism you can only infer from what I am showing you now. And what it is showing you outshines the entire universe for a few seconds. The strange thing is that this should feel limiting, and somehow it does not. The universe has constructed a situation where the most energetic event it is capable of producing is also the one that most completely hides its own workings. The engine is inside the explosion, and the explosion is inside a causally sealed region, and everything we observe is the downstream echo of a process that was already over before the first photon escaped. And yet, we figured it out. Not all the way, not down to the last detail, not to the level of direct observation, but far enough that we know the sequence, the mechanism, the characters in the story. A star, a collapse, a black hole, a disk, a jet, a burst, an afterglow, a supernova. And out there right now, in one of the 100 billion galaxies within our observable horizon, a star is probably running out of silicon in its core. A Wolf-Rayet star, stripped of its hydrogen envelope, spinning fast, low metallicity, the angular momentum of its core preserved through millions of years of evolution precisely for this moment. Its iron core is on the verge of the threshold beyond which neutron degeneracy pressure fails. In a few days, or a few years, or a few millennia, we cannot know the collapse will begin. The shock will form and stall. The outer layers will begin to fall inward. A black hole will form. A disk will form. Jets will launch and drill through the stellar envelope. And for perhaps 30 seconds, the event will briefly outshine every other source of electromagnetic radiation in the observable universe combined. A burst of gamma rays will propagate outward at the speed of light in a narrow cone. If that cone happens to point at us, if we happen to be in the beam, a satellite in Earth orbit, we'll register the alert in perhaps 1 billion years, or 2 billion, or 5. The light is already travelling. It may be in transit right now. We are watching the sky, waiting for receipts. The engine that produces them has always been invisible. The universe arranged it that way. And the most we can say is that we looked at the light, worked backward through the physics, and understood something true about a process happening behind a horizon we can never cross. That is not nothing. For a species that evolved on a pale blue dot orbiting an ordinary star in an unremarkable corner of one average galaxy, getting that far is extraordinary. Not as extraordinary as the hypernova itself, of course. But in its own way, genuinely something. The universe hid its most violent act behind the one boundary physics guarantees will hold forever. And we worked it out anyway, from the light that escaped just before the door closed. That, more than any energy number, is the part worth thinking about when you look up at the night sky and consider that somewhere out there, in the dark, behind an event horizon, inside a collapsing star 2 billion light years away, an engine is running that you will never see, and that if it is pointed at you, you will know about it, briefly and brilliantly, as a flash of gamma rays lasting about as long as it takes to read this sentence. And then it will be gone. And the universe will continue indifferent and extraordinary as it always has.